In this illustration, we intend to simulate the impact of one hollow sphere into the water surface in the Abaqus software. In this example, a hollow sphere with a mass of 2 kilograms with initial velocity equal to 4 meters per second hits the water. Since in this question the sphere is hollow and its density is less than water, it will come up to the surface of the water again after it has entered the water. In this picture you can observe the impact of the hollow sphere into the water, the formation of water, and the waves having been formed in it. I will enter the Abaqus software for simulation. I will click on Create Part. I intend to create the Eulerian part. I will select the modeling space as 3-dimensional. From here, select Eulerian, then extrude solid, enter the rough size of the tracing page equal to 5 and continue. I'll draw a rectangle, enter its length equal to 1.9 and its width equal to 1.4 meters. Then click on Done. Enter its depth equal to 1.4 meters. Here you observe the Eulerian part. This part includes two sections, water, void. Here we should distinguish the area where there is water and the area that is void. To do so, I will click on Tools menu, Datum, then select Plane and Offset from Plane. Select this plane, enter value, flip and OK. I will enter offset equal to 0.6 meters. Click on Tools menu, then on Partition. Here I will select Cell and use Datum plane. Select this plane and click on Create Partition. This area is covered with water and this area is void. I will click on Create Part. Here I intend to create geometric shape of sphere. I will select the modeling space as 3-dimensional. From here, deformable, then select shell and revolution. I will enter the rough size of the tracing page equal to 0.5 meters and continue. I will draw a semicircle, enter its radius equal to 0.1 meters, then complete the shape. Click on Done. Enter the degree of rotation equal to 360 degrees and OK. I will enter Property module. Click on Create Material. Here I intend to define the properties of water. I will click on General menu, then on Density. The density of water is equal to 1000 kilograms per cubic meter. I will click on Mechanical menu, then select EOS or the same equation of state. Then select USUP. The speed of sound in the water is equal to 1450 meters per second. Then I will click on Mechanical menu, select Viscosity from here. The dynamic viscosity of water is equal to 0.001 Pascal seconds. Then click on OK. Click on Create Material. I intend to define the properties of steel. I will click on General menu and then on Density. The density of steel is equal to 7,800 kilograms per cubic meter. I will click on Mechanical menu, select Elasticity and Elastic. Young modulus of steel is equal to 210 gigapascal and Poisson ratio is equal to 0.3. I will click on Create Section. Here I'll select Solid and Eulerian and continue. I will select Water Material and OK. I will click on Assign Section and OK. I will click on Create Section. Here select Shell and Homogeneous and Continue. I will select Steel Material, enter the thickness of the sphere equal to 2.04 millimeters. Click on Assign Section, select the sphere, done. Here select Top Surface and OK. You can observe the thickness of the sphere using Render Shell Thickness. Actually, the sphere is hollow and has been modeled with a thickness of 2.04 millimeters. In the next step, I will enter Assembly Module and click on Create Instance. Enter both parts into the Assembly section. Click on Translate Instance, select the sphere, done. First, select this point, then this one, and then OK. In the next step, I'll click on Translate Instance again, select the sphere, done. First, select this point, then this one, and OK. Here you can observe the final assemblage, and the sphere is exactly located in the center of the model. I will enter Step module, click on Create Step. Here select Dynamic, Explicit, and Continue. Time period is equal to 1.2 seconds, and OK. Then I click on Field Output Manager, Edit, enter the number of outputs equal to 120, and OK. I will enter Interaction module, click on Create Interaction, Contact, Continue, and OK. I will click on Create Interaction. Here select General, Contact, and Continue. Therefore, in this manner, the interaction between the sphere and water is defined. I will enter Load module, click on Create Load. Here select Gravity. I will enter acceleration of Earth gravity equal to negative 9.81 meter per second squared. Then I'll click on this arrow and select Whole Model, done, OK. In this manner, the weight of sphere and water would be considered here. In the next step, I'll click on Create Boundary Condition, select Velocity and Angular Velocity, and continue. I will select these surfaces, done, and close the boundary condition of V3 for them, and OK. Again, I will click on Create Boundary Condition, select Velocity, Angular Velocity, and continue. I will select the bottom of the model, done, close the boundary condition of V2 for it, and OK. I will click on Create Predefined Field, select Velocity, and continue. I will select the sphere, done, enter initial velocity of the sphere equal to -4 meters per second. In the next step, we should distinguish the area of void and the area of water. Actually, we should distinguish which section of the Eulerian part has been covered with water and which part is void. To do so, I will click on Create Predefined Field. Here select Other and then select Material Assignment and continue. I will select Eulerian part. Here I will select this area having been marked out by pink. Actually, the area having been distinguished by pink color is the area that is covered with water. I will click on Done and OK. Actually here there is water and here is void of any water. I will enter mesh module, click on seed part, enter approximate global size equal to 0.02 meters and OK. I will click on mesh part and yes. Then I'll click on assign element type, select the sphere, done, put the element library on explicit and OK. Here I will click on seed part and enter approximate global size equal to 0.015 meters, then click on mesh part and yes. As you observe here, more than 1 million meshes have been inserted on Eulerian part. Here I'll save the model. Here we can create a few partitions on the sphere in order to have a better way of meshing, and after that set to the job of meshing again. To do so, I'll click on Tools menu, then Datum. From here select Plane and then 3 points. Select these 3 points respectively. Then here select Point and Normal. First select this point, then this line. Here I will click on Tools menu, then on Partition. Here I'll select Face and use Datum plane. Select this plane and click on Create Partition. Then I'll select the whole of the sphere, done. Select this plane and click on Create Partition. Here I'll click on 3 points, select this point, and this one. Click on Datum plane. Select the whole of the sphere, done. Select this plane and click on Create Partition. I will click on Mesh Part and Yes. The question that arises here is that what is the mass of the sphere and how we can earn the mass of the sphere. Using the mass properties option, you can get the mass of the sphere. As you observe, here the mass of sphere is 2 kilograms. Actually, using query information and mass properties option, you can get the mass of the sphere. I will enter job module, click on create job. Continue. Here I'll enter the number of processing cores equal to 8. OK, and click on Submit. The analysis was done successfully, so I'll click on Result. In the example, a hollow sphere with a mass of 2 kilograms with initial velocity of 4 meters per second hits the water, and since the sphere is hollow and has a density less than water, comes up to the surface of water again after it enters the water, and this can clearly be observed in this animation clip. Here you can see the location of water droplets. A wave having been spread about can be observed, which is quite clear in this picture. Here we intend to obtain the velocity of sphere. I will click on Create XY data. Here ODB field output and continue. I'll select unique nodal, then select velocity directed at y-axis. Click on Edit Selection, select the whole of the sphere, and then click on Save. In the next step, I'll click on Create XY data, operate on XY data, and continue. Here I will select average operator, select all these velocities, click on Add to Expression, then click on Save As. Here you can observe the diagram of sphere velocity. The initial velocity of the sphere is -4 meters per second, and in these points, the direction of motion of the sphere changes. In fact, first the sphere moves downwards, here the sphere moves upwards. Again, it moves downwards and moves upwards again. In the next step, we intend to draw the diagram of the sphere displacement. To do so, I will click on Create XY data, select ODB field output, and continue. Here I will select U2, then click on Edit Selection, select the whole of the sphere, done, and click on Save. Then I will click on Create XY data, here operate on XY data, and continue. Here I will select average operator and select all the displacement cases. After that, I'll click on Add to Expression and click on Save. Here you can observe the diagram of the sphere displacement. First, the sphere moves downwards and penetrates to a depth of 0.35 meters in the water. Then the sphere moves upwards and downwards again and keeps in such a manner.